Hello everyone, in today's class we'll go through the material balance of a packed bed reactor. The packed bed reactor is similar to the plug flow reactor. The only difference is that it has packings inside the reactor, which is used to speed up the reaction time and increase the contact area between two phases. Similar to the plug flow reactor, we'll use a small differential section for the material balance. Okay, the small section will be filled with packings. So instead of dV, we'll be working with dW. The W is basically the mass of the packing inside the reactor. We'll also be solving for W instead of volume. W is the mass of the packing, and everything else is pretty much the same. The moles flowing in, moles flowing out. The only difference is the rate of reaction. For the packed bed reactor, we'll use Ra prime, which basically shows that the rate of reaction is in terms of mass. So usually the reaction rate units are moles per second meter cubed, but in this case it'll be moles per second kg. Okay, let me make this eraser smaller. So yeah, that's the only difference. So let's start with our material balance, which is input minus output plus generation equals accumulation. Our input is the mole flow rate flowing in minus the moles leaving plus rate of reaction prime, because it's in terms of weight, in terms of mass, times dW instead of dV, because we're solving for W, which is the amount of the mass of packing inside the reactor. Okay, so, and the accumulation is 0 because it's also assumed to be in steady state. So we can solve for dW by isolating it and putting it in one side. So Ra prime dW equals Fa minus Fa naught. This term here can be written as change in Fa, or dFA. Okay, so therefore Ra prime dW equals dFA. Isolating for dW, it equals dFA over Ra prime. Now the dFA, we need to change that in terms of conversion, because usually we're not given the final flow rate. Therefore we'll basically change it to the givens that we have, and usually conversion is given. So Fa equals Fa naught 1 minus x equaling Fa naught, if we times into the bracket, Fa naught minus Fa naught x. Now if you want the differential of Fa in terms of dx, it equals to 0 minus Fa naught. Therefore dFA equals negative Fa naught dx. We can substitute this term here and we'll get dW equals negative Fa naught dx over Ra prime. Now our equation of dW is in terms of conversion instead of Fa. Now the rate of reaction, as it's pretty much the same as we stated earlier in the previous videos. It can be in first order, second order, mix of reactants, But for the simplicity, as always, we'll use a first order rate of reaction. This negative here is because the rate of reaction is of A, and A is a reactant being consumed. Okay, therefore, also for Ca, we can do that down here. Ca equals Ca naught times 1 minus x. This is only true when we're dealing with liquid phase. For this example, for this derivation, we'll assume we're working with liquid phase. But for the gas phase, this equation is not true, and we have to use the expansion factor to find the concentration. So remember, this is only true in liquid phase. So we can substitute this also with Ca naught 1 minus x. Okay, therefore dW equals negative Fa naught dx over negative K Ca naught 1 minus x. Okay, we can also say that the concentration equals the mole flow rate over the volumetric flow rate. Therefore, Fa naught equals Ca naught times Q. Q is the volumetric flow rate. We can substitute that also in here. These signs will cancel out. Therefore, dW equals, instead of Fa naught, we'll use Ca naught times Q dx over K Ca naught 1 minus x. The concentrations will cancel out. We'll be left with dW equals volumetric flow rate over K dx over 1 minus x. We can integrate both sides. These are constant. They're not in terms of conversion. So they're not a function of conversion, so they can leave the integral. Therefore, W, which is the mass of the packing inside of the reactor, equals Q over K times negative ln times 1 minus x, which can also be written as W equals negative Q over K ln 1 minus x. And there you have it. That's your equation for a packed bed reactor with a reaction rate in first order. So that's your W, which is the mass of the packing inside the reactor. In our next video, we'll go through the expansion factor, which is finding the concentration, finding the final concentration when it's in gas phase. See you next time.